And we have our final speaker of the day is Chris, talking about leveraging Dask in YT.
Right. So I'm Chris Havlin. I'm at the University of Illinois in the data exploration lab with Matt and some of the other YT folks. And I'm going to share some explorations I've been doing over the past few months about leveraging Dask within YT. There's not going to be too many pretty pictures in here, but I hope it doesn't go too far into the weeds. So I hope I'll keep you entertained. So I'm going to give you a quick overview of kind of how YT deals with data chunking and parallelism. I'll throw out some ideas of how Dask might help, and then I'll show you some initial experiments, including a Daskified particle reader prototype, and then some work that I just started with using Dask and unit arrays to help in YT. Right, so in YT, when you do just like a load and a sample of a data, what YT does on the back end is it iterates through chunks, reads files into memory. So a single chunk is like a range of indices and data. It's potentially across data files, and YT handles all that on the backside. So you as a user don't see what's going on behind the scenes here. And so when you do something that involves operations across chunks, YT also handles that. So when you find a quantity like the extrema of a field, YT will go off to each chunk, find the extrema within that chunk, collect it across chunks, and then find the extrema of those extrema. And so when you use YT in parallel with MPI, it takes advantage of these chunks to do these parallel operations. So for example, if you're just finding the max density of a data of a field, YT will go off to each of those chunks. Those chunks get sent to different MPI processes, and then YT will collect the max from each chunk and then reduce it. And so this is great when you're doing a thing that YT knows how to do and has been programmed to do. But if you're doing something new that you want to do in parallel, it can be a little bit trickier. So yesterday we saw Ryan's talk, and he was describing some of his parallel workflow, and so you typically have to have a sense for how MPI communicates and splits things up. So you know, the example he showed was initializing the storage dictionary and then using the parallel objects iterations to put data into the storage, and then you have to do some sort of collection across the storage in order to do what you want with the data. So this is kind of where Dask comes in. So the question is, can Dask simplify YT's chunking and parallel processing? But first, let me give you the 2-second overview of Dask for anyone who might not be familiar. So Dask is a flexible library for parallel computing in Python. You can do lots of things with Dask. So this little GIF is just showing kind of one of the main ways that people use Dask using Dask arrays. So when you initialize a Dask array, Dask splits up a bunch of NumPy arrays into chunks. And so these chunks don't actually do any computation when you're defining the operations you want to do the chunks. It's just Dask is deciding how it will do the chunks when you want the data. And so nothing actually happens until you call compute on one of your chunks, and then Dask decides how to properly reduce across all your chunks and give you the answer you want. And so to do things in parallel, you just have to initialize this Dask distributed client. So you initialize a client with some threads, some workers, and then when you initialize these arrays, they get sent to those different processors. And so when you actually do your computation, that computation happens on all the different processors, and Dask handles all the collection, and it's great because you don't have to think about it. And then the final way that not the final, but one of the other ways that is relevant, I think, for the discussion here is the use of Dask delayed. So this is a slightly more general way of defining parallel workers. So you have a list of tasks that you want to set up a task graph for, which is how Dask decides how to do things. And then you just use this Dask delayed decorator in order to set up your parallel workflow. So in this pseudocode example, there's this loop over dataset chunks. So this could be, for example, the chunks of a YT dataset. And so for each chunk, we're going to decorate some function that's operating on a chunk. And so we want, this could be a complicated function, could be some sort of collection, min max, or some file input output, and you get a result. And Dask has not actually done anything yet other than write some code to tell it how it will compute the answer. And so for each chunk, we add a delayed task to a list. And then when we actually want the answer out, you just call dask.compute on those delayed tasks. So this is just a kind of a simple way that you can define parallel workflows and let Dask do all the decision making behind the scenes on how to actually compute things. So can Dask simplify YT's chunking and parallel processing? Yes, I think it can. Two main ways. So for developers of YT, I think it could provide some significant code-based simplification in that to write things that operate in parallel, you don't necessarily have to go into a bunch of MPI communication protocols. And on the user side, it's simpler to get Dask up and running than it is for MPI, I think. And it's just a pip install Dask distributed. And then it's also simpler to design new code that will work in parallel, I think, for your kind of average Python user. So, okay. So I'm going to give you a quick overview of this notebook I have here, which is a prototype of a particle reader that works with Dask in order to just read in particle data. And so this, I'm not going to actually go into this code, the actual code too much here, but so this is basically rewriting the read particle selection of YT's base IO handler. And so this works for gadget data sets, at least, perhaps others. But I'm only going to just highlight down here. So the actual Dask bit, the important Dask bit, is this loop in here. So for every particle type you want to read in, it sets up a set of delayed chunks. And so for each of the chunks, there's this iteration over chunks, it decorates this reader function and provides the arguments you need to that reader function. So it's the chunk you're working on, some information about the particle types, the selector object, if there is a selector coming in like a sphere or another geometric selector, and then it sets up that chunk. And then down at the end of here, when it's actually ready to read those in, it'll call the compute in order to get the arrays out from each of those chunks. And so this does work.
Chris, sorry to jump in. So you have officially you have like 3 minutes left before you start bleeding into question time.
Okay, great. Right. So so in this example, so you can do an import YT, typical loading of a gadget data set. And so when you actually pull out the field here, it'll actually use Dask to read in those chunks. And so in order to do this in parallel, all you have to do is import a client, spin up a client, and the syntax is exactly the same, except now that IO will actually happen on different processors, and Dask will collect it all and give it to you at the end. And so, and then this is just a screenshot of that happening on the different processors, so the different read times for some of these reads. So that's cool. It's kind of a good start for getting stuff into Dask. But one of the things it does right now is it returns things into a dictionary of normal arrays, because YT will, when it comes out of this function, it'll convert it into a YT unit array. But what if we didn't do that? So if instead of actually returning a memory array, if we returned a reference to the Dask array for the user, when you do something like this, when you pull out density, then you could do normal Dask operations on those fields you pulled out in parallel. So you could very easily define your own parallel workflows afterwards that may not have a program solution in the YT code base yet. And so something like Ryan's workflow could look a bit simpler, where you do more of a simple kind of pull out all the data, and then you get your parallel Dask arrays, and then you have some complex function that does something, gives you some new answer, and then you can use Dask to save that Dask array to an on-disk storage, and everything will happen in parallel or in serial with the same syntax. Right. So one of the caveats to all this is our unit arrays, because YT does work in unit array, and so in order to really get this functionality working, you have to think about having a Dask unit array. And so I started working on this a few weeks ago and thinking about how to do this. So Dask provides ways of implementing your own classes for custom collections. So a collection is a thing that works with Dask. It's the base class for the Dask array. And so in the simplest way, you would just subclass this Dask methods and we'd create our own unit Dask array. But because we want array functionality, it actually makes more sense to try to subclass Dask's existing Dask array, because then we don't have to rewrite all of the reduction methods that Dask has implemented. But also, we don't want to use the unit functionality. So somehow in our unit Dask array, we have to keep all the unit operations. Right, and so I'm going to show you in just an initial usage of a class that kind of works, just as a proof of concept mostly. So this class here is inheriting from array, which is the core Dask array, and so it does some stuff. I'm not going to get into it now. I will send the links to these notebooks afterwards if you want to go into detail. But so you can define using this unit from Dask function. You give it a Dask array, your units of your initial unit array, and you get out something that behaves as a Dask array. So if we want to actually get our values, though, you get out a unit array in the end. And so you can, let's see, raise it to a power, take a min, oops, compute it, and you see the units are right. We have our min value. That's all well and good. And you can, let's define a second Dask array. So when you multiply the two arrays together, let's take a min along an axis and then compute it. We see we get that's something. Oh, right, because I actually, so there's a little bit of an issue here where the way the class is working right now will actually store that unit change in place rather than giving you a new value. So we have meters cubed instead of meters squared. But so it kind of works. It's right now, though, one of the disadvantages is that right now I have to actually go in and catch all of the NumPy array protocol universal functions, because unit and Dask have slightly different ways of implementing those NumPy array protocols in order to catch the different calls and attach what they need to. But hopefully that'll be better automated so that I don't actually have to go through and rewrite all of the different methods in order to do both the Dask and the unit operations. But one final note that I'll say is that one of the cool things about this is that when you change, right now we have units. So when you change the units and do unit conversions, nothing actually happens on the Dask side. It's just tracking in some hidden unit array attributes within this new class. So you can do all these, you can chain together a bunch of different unit conversions, but nothing actually happens with Dask until you do that final compute, and you should get out the final units that you set it to. So it's not, because Dask doesn't actually have to need to know this magnitude of your units in order to do those collection operations. But yeah, so that is that. And I'm at the end. So there's still a fair bit of work to do with these Dask unit arrays. And then once that's working, I'd like to extend it into the particle reader prototype that I have and think about chunking operations outside of particle input output. And then also I'm going to need some more community input here, because I've kind of just been working in my own space, just learning how YT works. And figuring out how to get Dask in there. So there will be a YTEP at some point, but I will solicit some input before that's even written probably. So let me stop there.
Thank you so much. I'll clap. Apologies for having to turn off my screen. My internet's a little slow. This is so cool. I think you may like revolutionize everybody's workflow here. So thank you. I'm getting there's some questions in the chat that I feel like I can just like read. Please raise your hand if you have one to say. Joseph Burchett is asking, do you know the bottom line load time improvement from that gadget example you showed earlier, loading like some data attribute?
Yeah, so right now I'd say it's not much of an improvement in load time raw. But I haven't done any Dask optimization at all. There's a lot you can do with sort of telling Dask how it should distribute data and or to load balance those different processes better. But it's really about the same time as a normal load. I also was working with a pretty small data set, so I haven't actually tested it at scale on larger data sets where I think you'd see more improvement. Yeah, but it's a good, important question for sure.
Yeah, cool. And then, okay, I lost a little bit of the thread. Matt, do you think you could say kind of what you were saying with Josh's question and your build on it?
Yeah. So Josh, pointed out that having the Dask unit array would be really awesome. I think so too. Do you think that would have to be something incorporated into mainline unit, or could it be a Dask unit package / plugin or something? I'm just wondering from like a software engineering perspective, does that need to be?
I don't think it needs to be, because it's not really adding new array functionality to unit arrays. It's okay, because at least the way I've built that initial prototype class, it's kind of just operating with unit arrays in these hidden attributes underneath the main class. So it could easily be a plugin or a separate package that you use on top of unit array and Dask. But yeah.
Cool, that's awesome. Okay, I don't see any other hands, but remember, if you come up with a question, put it in Slack so we can all think about it together. Great, thanks so much for that talk, Chris. Thanks so much for the other talks this afternoon and all day. This was so fun. I have really enjoyed learning all this stuff about YT and other extensions and uses. So that ends our day. Thanks so much for attending day 2 of Rhythm, and I will see you tomorrow morning, bright and early for some, perfect timing for others, super late for others. So sign on if you're able. See you tomorrow.